we need to, if we detect somewhere in the heap, the binary tree that violates the max heap property. Here we call the max heap property. So that property, it means the value of the parent node should be greater or equal to the value of any of its child. That property, if it is violated, we need to fix it. How to fix it? We have that max heapify operation, swap, so, find the largest value in a local area among three nodes, parent, left child, right child, then do one swap operation to fix it. Okay, all right, So now we can work on one simple example. Okay, so let's start with this example. Okay, so last time we work on this example. Here you can see around these three nodes, the max heap property is violated because the value of its left child is 14. It is greater than its parent node. The value of its parent node is 4. All right, So how do we fix it? First, let's find the largest value between left child, right child, 14, 4. So this is the larger one. Then we swap value of these two nodes. Okay, so after one swap operation, we get the current heap like this. But when we move that node with value 4 down, we may have another violation around these three nodes, another possible violation. So we need to check it. Here we get this violation, because this value 8, its right child value is greater than the parent value 4. So we need to do another swap operation between these two nodes. And finally, this, look at this node with value 4. When it reaches the bottom, we're done. So we do not need to do any further operation because this, we can, so if you like, we can call this node, where the violation occurs, this node, the dirty node. Okay, although in the textbook, nobody calls that, but in another different context, so, another different context, when something is wrong somewhere, so we call it, dirty thing, a dirty bit, dirty, something is wrong, so that concept, if we use that concept here, we can call the node where a max heap property is violated, we can call it a dirty node. So this dirty node, when we do the swap operation, we move the dirty node down the tree along certain path. But we need to keep track of this dirty node. Okay? Everywhere it goes, we need to do the checking. Do the checking around 3 nodes. the dirty node, its left child, its right child, and look at if there is any violation, max heap property violation. If no violation, we can stop. If no violation, then that's all we need to do. We can stop. But if there is a violation, we need to run that max heapify operation to fix it. But when we fix that local area, we move that dirty node down the tree another level. So we need to follow that dirty node down the tree and do another checking until we reach the bottom, until that dirty node reaches the bottom of the tree, so we can stop. All right, so that's the whole procedure. So that is the max heapify operation. Yeah, because this operation is a basic operation for us to manage the max heap structure. Yeah. So that is very important. Later, when we do, any insertion, deletion, sorting, we rely on this basic operation, max heapify operation. Okay, yeah. All right, so that's, so we spent some time to understand this operation well. So next, we can talk about next part. Yeah. Next question. All right. Yeah. Yeah. All right. The next part we want to do building a heap. Yeah. Given an array at the beginning, it's not a heap. It's not a, let's say, not a max heap. Okay. It's not a heap. We need to make it a heap. Yeah. Here, because we only studied a max heap, here we consider building a max heap. Okay, building a max heap. Yeah. How to do it? Still, that max heapify operation, that basic operation we need to use to build a max heap. Yeah. All right. I just run a simple example, so you will get the idea. Yeah, how to build a heap. Yeah. All right, so when we start, we are given an arbitrary array. Yeah, like this. Yeah. All right, so now our goal, we want to build a max heap. Yeah. So we need to do swap operation, max heap. Yeah. But when we start, first, we need to arrange these values in a near complete binary tree structure. Yeah, near complete binary tree. Yeah, because the heap needs to use this structure. Yeah. All right. So visually, let's arrange in this near complete binary tree in this way. Yeah. All right. Just follow the natural order. 4, because its location, yeah. First node, yeah. Location 1, then location 2. Yeah. So here, yeah, we can imagine, we know location 0 not used. Yeah. So here we can just imagine there is unused location 0. Okay. So then 4 corresponds to location 1 in the heap, and location 2 in the heap, location 3 in the heap. Just arrange them in order. 4, natural order. 5, okay. 6, 7, in this order. 8, 9, 10. All right. Definitely, it's not a max heap, so we need to fix it. All right. So when we fix it, yeah, here, let me just erase this location number. Otherwise, you get confused. Too many numbers, all right? Yeah, so you know, yeah, that natural location number. Now, we don't need it, need them, all right? But when we do the fixing, all right, so we start checking, bottom up checking. So we do checking max heap property violation. Yeah. So here, yeah, let me just write something to give you some basic information here. Right? Yeah. After the arrangement, yeah, first, yeah, let me write. First, arrange the nodes in the natural order. Yeah, so this step very easy. All right, so check that check for any violation of the max heap property. In bottom up way. Bottom up way. Okay, all right, so what's the bottom up? Yeah. We start from the end of the heap in local region like this. Okay, yeah, because this local region, there is no right child. Yeah, so only two nodes we do the checking. All right, no violation, it's okay. Yeah, we move to the next one. All right, this local area, there is a violation, right? Yeah, so the value 2 is less than that value 14. So we need to fix it. We need to run that max heapify operation to fix it. Okay, all right. So let's run it. Yeah. After one swap operation, we fix it, right? We fix it. Then we move up. Okay, this 3-node local region, we move it up. And we detect another violation. That means we need to do another max heapify operation by one swap operation to fix it. Okay, yeah. After that, it is fixed. We move up or move to the left to another 3-node local region and check for the max heap property violation, another one. So we need another swap operation. But when you fix it, remember you need to check, move it down to the tree until you reach the bottom. Okay, yeah. So not just one swap. You may need to do several swap operations. All right, yeah. So after you fix it, this value 1 node is at the bottom of the tree. Yeah. Then you check the last 3-node local region because you reached the root. Yeah. So you get a violation and swap value 4 and value 16, but you need to, move down the tree, all the way down the tree, and possibly you may reach the bottom until you fix all the violations down the tree. Yeah. All right. Yeah. So here you move node 4 one level down, but another violation, right? This violation, you need to fix it. Okay. Yeah. Swap and then another swap. Yeah, because after you move value 4 down, another possible swap. And at the end, you get this binary tree structure, and you can see there is no violation anymore. Everywhere, we have that max heap property. Okay? And we get that max heap structure. We complete the building step in this way. All right, yeah. So you can see we follow procedure like this. Okay, yeah. Bottom up way. Every time we check 3 node local area. Yeah, sometimes we don't have right child. Okay, yeah. That triangle, yeah, that little triangle. Sometimes we don't have the right child. Yeah. And then we move from bottom up, but in the same level, we move from right to left. We start from the rightmost location, and then we move from right to left. Then, after we complete one level, we move one level up from right to left, and so on, until we reach the root. When we hit the root node, then we run that last max heapify operation, but we need to move that dirty row down the tree and do the checking all the way down the tree until we fix all the violations, all possible violations. Okay. After that, we get a max heap structure. So that structure is used to maintain the dynamic data. Maintain the dynamic data. Now, what do you mean maintain the dynamic data? Because that structure is very useful. With that structure, if we need to insert a new node into the tree, after insertion, we know the max heapify property may not be valid, right? The max heap property, we need to fix it. The fixing step, log base 2 of n. Yeah, so that's what we need. Yeah, the fixing step, log base 2 of n. Okay, yeah. This is the one when we design the data structure, we want this property. Yeah. Fixing operation. After deletion, we also need to fix it, right? Yeah. And the fixing cost, log base 2 of n. That's the one we like to have. Okay, yeah. All right. Let us continue. Yeah, all right. So here we complete last lecture. Yeah, so we need to start our new lecture today. Yeah. Part B of Module 5. Yeah. All right. Yeah. Next, we need to calculate the building cost of a heap. Yeah. We just build a heap, right? What is the cost building a heap? Yeah. If it's too expensive, then we may not be we may not want to take it. If the cost is too high, we may drop this method. Okay, yeah. So we want to make sure if the cost is acceptable or not. Yeah. So let us estimate the building cost of a heap. Okay, all right. Yeah. Combine the cost of all heights. Yeah. Because we run that max heapify operation level by level. Yeah. And each level, each location, we run the max heapify operation down the tree until it reaches the bottom. How much is that cost? Yeah. How much is that cost? We need to calculate that. Yeah. So that's the reason here in this title, combine the cost of all heights. Yeah. For each height number, yeah, height, yeah. So here we use this height concept. Yeah. What is the height, right? So some of you may like to know what is the meaning of the height. Yeah. All right. So let me use the example to show. Yeah. What is the cost mass heap, right? So here, yeah. What's that? Yeah. Let me. Yeah. Because I need to right. B.2. You know that. Yeah. I need to move to the very beginning. Right. Yeah. Heap nodes in each level. Yeah. Because we need to start from the very beginning. Yeah. All right. Then we can calculate the building cost for each level. Yeah. All right. All right. So number of leaves in a heap. When we start, we go level by level, bottom up way. When we start, we want to start from the very bottom. Okay. In the very bottom, we have this concept, the leaves, the nodes at the very bottom, we call them leaves. Yeah. Leaf node. Yeah. Here, these nodes are leaf nodes. So those nodes without any child. Yeah. Each node, there is no child for the leaf node. Okay. So we call the leaf node. Tree, leaves of a tree, right? So we use that concept. So we define the nodes in the tree that do not have any child node. We call the leaf nodes. Okay, yeah. All right. So here we want to count the number of leaves in a heap. Yeah. All right. All right. Nodes without children. That's the definition of leaf nodes. or leaves. Okay, all right. Yeah. But here we want to do the calculation. How to describe a leaf node? How do you know a node is a leaf node, right? Yeah. So given a heap, and if the index of a node is given, array index of that node is given. Okay, yeah. How do you know that node corresponds to a leaf node? Yeah. All right, so here we answer that question. We look at the parent-child relationship. By the definition, we know a leaf node does not have any child. A leaf node does not have any child. But how do we represent this fact? When a node does not have any child, how do we know it? How do we know a node, if a node has any child or not? Yeah. So we look at the parent-child relationship. We know when a parent corresponds to this array element, A of I array element, then if it has one child, we know when a node has, we consider child nodes, it may have one or two. Yeah. But first, we should have the left child, right? Then second, right child. Yeah. So here, we can consider its left child. Yeah. Because its right child sometimes may not be available. Yeah. So to be safe, we just consider if it has a left child node, right? Yeah. A of 2i corresponds to its left child element. Okay, all right. Now, we just check if there is this relationship. Okay, if the parent, if this node is a leaf node, if the parent is a leaf node, that means A of 2i is not in the array, right? A of 2i is not in the array. If it is in the array, then by the definition, this node has a left child, and this node cannot be a leaf, right? So it does not follow the definition of a leaf node. Okay? Yeah, so based on that logic, this location, this location must be out of bound, out of the bound of the array, out of bound of the array. Yeah. So what is the bound? So remember, we want to use the array location. Yeah, here we skip location 0, location from 1 through n. That is the value locations we use to store heap elements. Now, out of bound, that means 2i is greater than n. Greater than n, out of bound. All right, yeah. So meaning of no child, we want to use an inequality to describe the meaning of no child. That is the condition. I less than equal to n, yeah. I is within the bound. Yeah. I, yeah, because that's a valid node in this heap. I is within the bound, less than or equal to n, but 2i is out of bound. 2i is greater than n. All right? Yeah. So this inequality provides us the description we need for a leaf node. All right. Then let's do some simplification. Yeah, so this index range, yeah. After division by 2, we have this n over 2 less than I. Okay, yeah. This simplified inequality. Okay, yeah. Then, because n over 2 may not be an integer, right? Think about that. N over 2 may not be an integer. So we want to improve the accuracy of this inequality. How to improve it? Yeah. The smallest such I that is greater than n over 2. Yeah. So if we use integer representation to improve this inequality, yeah, we can use this floor function plus 1, because strictly, look at that, strictly greater than n over 2. Not, there is no equal case, strictly greater than 2. That means even when n over 2 is an integer, I still strictly greater than n over 2, that integer, right? So the smallest such I can be represented as the floor function of n over 2 plus 1. Yeah. All right. Now we find the range for the I. I is the location number for a leaf node. A location number, yeah, we can also call its index. I is the index number of a leaf node. Its range is between these two numbers, less than equal. Yeah. So that's the best we can do to describe the range of a leaf node. After that, we can do the counting. Count. How many nodes are in this range? Yeah. How many eyes satisfy this inequality? Okay. Yeah. Can we do the counting? Yeah. The upper bound and the lower bound. Upper bound and the lower bound. Yeah. Think about the difference of upper bound and the lower bound. The difference, right? Yeah. But the answer is n minus the floor function of n over 2. So remember that this plus 1, we need to include that number. Plus 1, we need to include that number. Yeah. Here, let me draw a diagram here. All right. Suppose this line represents the whole array. The upper bound n is here. The lower bound floor function n over 2 plus 1 is here. Okay? Yeah. I falls into this range, including these two boundary numbers. Okay? Including these boundary numbers. Now we want to count how many integers are in this range, including two boundary numbers. We do subtraction. When we do subtraction, we use the upper bound to subtract the number that is 1 less than the lower bound. 1 less than the lower bound. Okay? Yeah. 1 less than the lower bound. What's that? That's the floor function of n over 2, the subtraction here. Okay? That's the subtraction. subtraction, we do, n minus floor function of n over 2. Okay, all right, So we get this number. This number represents the number of leaves in a heap with n nodes. Okay, all right. Next, we can do some simplification. So this is the simplification. This simplification is based on an equality in our textbook. So here, let me erase this part. Let me show in our textbook, we have this equality. Okay, on page 477, Then n minus floor function of n over 2, so we get the ceiling function of n over 2. So you have another way to represent number of leaves in this way. Okay, so we answered the first question. Number of leaves in a heap. We answered this question. This is the answer. Sometimes we use this expression, sometimes we use the second expression. Okay, either one is fine. Okay, all right. Next, because if we only look at the leaves, that's not enough. We want to move level by level higher in the tree. So we consider nodes with height 1. What are nodes with height 1? Look at these 3 nodes in the tree. They have height 1. How do we define height? First, we look at the bottom level, the leaf level, the bottom level. Bottom level, we treat them at the ground. So ground, we call height 0. Ground level, the height of the ground level nodes, the height number is 0. Okay, ground 0, right? But when you look at these nodes, they has one edge reach to the ground. That is the height. The number of edges in the path, you go from one node to the bottom, that number is the height number. Okay, all right. But what is the height of this node? Because if you're along this path, there are 3 edges. If you go along this path, there are 2 edges. 3 to, different. You take the longest path. When you count the high number, you take the longest path from the current node through the bottom level. So that's the way we define the high number. Okay, all right. All right. So now we want to count the number of internal nodes. Here, another concept. What's the internal node? Internal node, those nodes that are not leaves, we call it internal node. Okay? Leaves, sometimes people call external nodes. External nodes, the same meaning as the leaf nodes. So the nodes, or you can say the nodes that have child nodes, we call it internal nodes. okay? Or you can say all the nodes that have height greater than 0. Yeah, so internal nodes, their heights are greater than 0. Yeah. So you can understand in different ways internal nodes. Yeah. So this time we want to count the number of internal nodes with height 1. How do we describe this property? Okay, yeah. Because here at this point we have the experience to describe the number of leaves. So we just use the similar way to describe those nodes with height 1. Okay. Now, pretty straightforward. Yeah. All right. So let's start. Yeah. All right. Number of all internal nodes. Yeah. So before we start, yeah, we can find this number easily. The number of all internal nodes. The total node number is n, and we also know the number of leaf nodes, n minus floor function of n over 2. The difference is the number of internal nodes, right? Yeah. So what's the difference of these two numbers? Floor function of n over 2. That's the difference. Yeah. So this number is the total number of internal nodes. Okay? Yeah. Yeah. Here you can see for the number of leaf nodes, because we know this number equals ceiling function of n over 2, and the total number of internal nodes, this expression, can you see the ceiling function is greater or equal to that floor function? The same n over 2, but one is in ceiling function, the number of leaves, one is in floor function, the number of internal nodes, and the ceiling function one should be greater or equal to the floor function one, same number, n over 2, right? Yeah, so that property, easy property, okay? All right, now let's count the number of internal nodes with height 1. How do we describe it? Yeah, all right. We just look at their children. If a node has height 1, then its left child node, yeah. Its left child node must be a leaf, yeah. Because we do not know if it has a right child, but we know it must have a left child, right? So we just look at its left child. Its left child must be a leaf. That simple observation, right? Yeah. All right. So now 2i, that's the index of its left child. So 2i is the index number of its left child node. And it must be a leaf. We know the range for a leaf node is this inequality. That's the range for a leaf. Okay? Then we simplify this inequality and we get this inequality. Okay? Yeah. The right-hand side is relatively easy. We do division by 2 and then take the floor function. But the left-hand side, why it is correct at the left-hand side? Now, that is a little harder to see it. We need to do some calculation. We need to prove this equality. This is an equality, okay? Yeah. Because the left-hand side, we take the ceiling function of, yeah. So this number do division by 2, then take the ceiling function. And we can simplify to get this expression. But the question is, how do you see it, right? Why it is correct? Yeah. Here, you can prove it in this way. Okay? Yeah. Yeah, because this expression here, it is just n over 4 flow function, right? Yeah. So you just consider the cases. N is a multiple of 4k. Yeah. N is 4k plus 1. N is 4k plus 2. And N is 4k plus 3. You try these four cases, you check this inequality for these 4 cases. You can see all of them are true. So you plug in N equals these 4 different expressions. You can see all of them are correct. So you get this equality. Then we use it, we can get a simplification like this. All right. So that is for the height 1 range, index number for the height 1 range. Okay, yeah. Then the next thing we like to do, how many of those numbers? How many nodes are in this range? Do subtraction as we did before, the upper bound minus 1 less than the lower bound, right? Remember, 1 less than the lower bound minus that number. Okay, yeah. So that number, the answer, number of internal nodes with height 1, the upper bound, that is flow function of n over 2, minus 1 less than the lower bound. That's the flow function of n over 4, 2 squared. Yeah, okay, yeah. That's the final expression of the number of internal nodes with height 1. Okay, yeah. And if this number is less than or equal to seeding function of n over 2 squared. Yeah. This time, it's not exact equal. It's less than or equal. Yeah. Because sometimes it's strictly than. It's not equal. It's not always equal. That's different from the leaf case. The leaf case, we have equality, always equal. But this one, other than the leaf case, with height greater or equal to 1, we have inequality when we try to use the seeding function expression. Yeah, because we can use these 4 cases to check. We can find at least one case the inequality is correct. Equal sign is incorrect. We can find them at least one case. All right. Yeah. Here I do not check it. All right. Yeah. So that's the answer. Yeah. Don't forget when you use the seeding function expression, that's inequality. Yeah. Sometimes we can use inequality. Okay. Yeah. All right. Next, the next step we need to do number of internal nodes with any height. Any height. Yeah. Because after this number counting, then we can estimate the cost building a heap. But for the any height, so we can quickly get the answer from our current experience. We generalize the previous result. Yeah. The number of leaves, yeah, we already have it, this expression, right? Yeah. Height 0 case, yeah. Then height 1 case. the number of nodes with height 1, that's this expression, and the counting number is this expression. All right, that's the height 1 case. Can we use the similar expression for any height number here as the generalization number of nodes with height h? Okay, so if it's a high h, let's write high h expression. Okay, first, the range for high h node is this inequality. Okay, so look at the height 1 expression. 2 to the first, right? The right upper bound n over 2 to the first. So the generalization 2 to the h power of 2 number. Okay, so that's that kind of relationship. The lower bound, the floor function n over 2 to the h plus 1. 1 plus 1, 2, that's 1 plus 1. Okay, so then plus 1. The range generalization. Okay, all right. Then the number of nodes in this range, we do subtraction. Upper bound minus the number 1 less than the lower number. So this expression, that's the counting number. Number of nodes with height h. Okay, all right, before we move to the next one. And this number, similar to the high h case, this number is less than or equal to the ceiling function of n over 2 to the h plus 1. Less than that. Because later, when we estimate the total cost, we need to use this inequality, the ceiling function expression, when we estimate the total building cost. So we need this expression. Okay, all right. So we complete B.1, B.2. Now we can calculate the building cost of a heap after we do the preparation, counting the number of nodes with different height number, starting from 0 through the highest possible height number. All right. Combine the cost of all heights. Now we get to this point. Combine the cost of all heights. Okay, the cost of max heapify for all nodes of height h. What's that cost? Suppose we want to fix the max heap property violation at the node with height h. How many swap operations you need to do? We have this expression. Ceiling function of n over, but this is the number, right? So this expression, this is the, upper bound. Great. This many, we know the nodes with height h, that number less than or equal to this expression. Okay, so we just derive it from B.1. Okay, all right. Then to fix it, we need to move from height h down to the bottom, right? The bottom is the bottom level, height 0. Height 0, that's the bottom. Okay, we move from high h to high 0. How many steps we need to move? Right, h step, right? At the most h step. because you reduce every time you do one swap operation, you reduce the height by 1 from h to h minus 1, then from h minus 1 to h minus 2, and so on. Then after you reduce h times, you get to height 0. Okay? Yeah. So the cost, you need to use big O of h. That's the cost you may need to take, a big O of h. Okay? All right. Yeah. That's because this number is for one such node. One such node. But you have this many such nodes. This many. You do multiplication, right? You do multiplication. All right. So here, the heights from 0 to floor function of natural log of n. Yeah, floor function. Yeah, so this is the height of the root. This number is height of the root. Okay, yeah. Floor function of log base 2 of n. Okay, yeah. All right, yeah. Because from 1 to the height of root, you 0 at 0, you do not need to do anything, right? 0, yeah, 0, you do not need to run the max heapify operation at the ground 0, height 0, okay? Because they're already at the bottom. You do not need to fix anything, right? They're already at the bottom, yeah. So when you start, you run the max heapify operation from height 1 nodes for all the height 1 nodes. Yeah, so that's why the height should go from 1 through floor function of log base 2 of n. Okay, yeah, all right. Yeah, so here we skip the leaves, yeah, because no fixing operation for leaves. So that's the reason we skip them, okay, all right. Then we write the summation of the total cost. So this is the summation of total cost, okay, yeah. This number, we know the number of nodes with height h, that number. Then for each such node, we need this much cost to fix it, to fix the possible max heap property violation. So the total cost, so this is the total cost expression. Okay, total cost, total building cost expression. The next thing we need to do, we need to simplify. We want to find a simpler expression for this big summation. Yep. Because this big summation, we cannot see how large it is. We want to simplify it. Okay, yeah. So our next thing, when we do simplification, we use inequality because the seeding function is less than, after we remove the seeding, we plus 1. You know? So you plus a fraction less than 1, right, to get a seeding function. Yeah, but for simplicity, we just plus 1, we get a larger expression. For each term, we remove the seeding function and by adding 1 on that function inside the seeding function. Okay, yeah, all right. Then that summation, we can simplify, we can write it in 2 summations. Yeah. The first one, that big O, so this one times that H, yeah. The second one, 1 times that big O, okay? 2 summations. Yeah. But this one is very simple, right? Yeah. The second summation is simpler. Yeah. The second one we can calculate easily. Yeah. Because just sum of the consecutive number from 1 through floor function of log base 2 of n. And we have this formula. This formula. 1/2 log base 2 of n times log base 2 plus 1. Yeah. Although we should use the floor function, yeah, but here we remove the floor function. That difference is so small, so we don't worry about it. Okay, so we like to remove the floor function to get a simpler expression here. Okay, all right. And this one, yeah, because this plus 1 is not important. We just ignore that plus 1. We get a bigger of log base 2 of n squared. Yeah, that's for the second summation. Log base 2 of n, and it's squared here. All right. So then next step, we want to estimate the main summation term. That's the most important part. Okay, yeah. All right. To estimate this number, we can take that n out. That n, in all these terms, that n never changes. So we can factor it out. Common factor, and we can factor this common factor number n out of the summation. Okay, so we only need to calculate that's the remaining terms inside the summation. Okay, yeah. But how to get that? Yes, the upper bound of the summation, log base 2 of n, that's not convenient to handle. So we replace it by infinity. Yeah, we are more generous, right? We add many more terms. Yeah, we are very generous here. We relax the upper bound of the summation to infinity. So we should get a larger sum, right? Yeah. Now let's look at even we relax the upper bound to infinity, the summation number still under control. Yeah. So let's calculate that number. Then we complete it. Okay. Yeah. So let's calculate the summation of this form to infinity. There are infinitely many terms here. Okay. Yeah. And to find the sum of the summation, there is a smart technique we can use, a very smart technique. Yeah. Otherwise, if you do not apply some smart technique, it's not easy. Yeah, it's not that easy. Okay. All right. Let me leave this part next time. Okay. The summation next time, yeah, because we run out of time. Yeah. All right. So next time we find the summation, we can get a total building cost of the heap. Then after that, we can run the heap sort. Yeah. After that, we are ready to run the heap sort. So we just complete the heap sort after that. Okay. And we can also estimate the total cost of heap sort. Yeah. Those things are pretty easy to get. Yeah, just a few more steps, we can get everything we need regarding the heap sort. Okay? Yeah. All right, so next time.